Yeah, good afternoon. Welcome to Hong Kong University. And this is a function organized by the Center for Water Technology and Policy. The Center for Water Technology and Policy was established last year in May. And it was funded by two local foundations. And it's supposed to be a first of its kind. It's an interfaculty collaboration. So it's a faculty of social sciences and the faculty of engineering. And we are collaborating. So I've been talking to engineers whom I've never talked to, okay, all these years I've been teaching here at Hong Kong U, yeah. So I'm based at the Faculty of Social Sciences. And today we are very pleased to have a prominent engineer from the United States, Professor Sattler from the UC Berkeley, University of California, Berkeley. He's the center for the, he's the director of the Water Center at UC Berkeley, yeah. And now, we also have two very distinguished local speakers, and they will be the discussants. We have the Deputy Director from the Water Supply Department, and we have an adjunct professor from the Department of Engineering. So, Professor Sattler, just introduce you. Yeah. This one. And then we're going to have a group photo taken. So, Alan.
Well, thank you. Good evening, everyone. Thanks for coming. When we first started talking about this event, we thought we'd do it on World Water Day, and then we realized that was Friday. And it's a lot to ask of people to come to a public lecture on a Friday afternoon at 4 o'clock, and we thought Wednesday they'll stay awake. Wednesday they'll be engaged, and Wednesday they won't be looking at their watches and thinking about when they're going to go home. So here we are Wednesday, but pretend it's Friday and it's World Water Day. Now, I've been here two previous times giving talks, actually. I think it was in this lecture room or maybe the other one the last time. And the first time I was here, I talked about an idea called Water 4.0. And the idea behind Water 4.0 is that there are revolutions that happen in urban water systems, and that we're going through what I refer to as the fourth revolution, a period of major change in the way in which we deliver water to cities. And then I came back last year in the spring, and I gave a talk about the progress we're making on Water 4.0. And I told the story about how the drought in California and in Texas and the Colorado River Basin is causing Water 4.0 to happen in the West and Southwestern United States a lot faster than anyone thought. And when you look around the world, you'll see that that revolution is essentially complete in Israel and parts of the Middle East. It's made a lot of progress in Singapore, and even in Australia, there are cities like Perth where most of the drinking water now comes from seawater desalination. And so in some ways, Water 4.0 is a completed story, and it's time for us to turn it over to the practitioners and the engineers to actually build it. But there's a caveat there. That's water in rich cities. So if you look at all the cities I was talking about, the Southwest United States, like Los Angeles and San Diego and San Francisco, or Singapore or Perth, these are places that are wealthy. And so Water 4.0 is water for some. I don't want to talk anymore about water for some. I want to talk about water for all. The people who live in cities that aren't as wealthy, and I want to think outside of the city. I want to think about people living in the rural landscape where agricultural water use is the real concern, not necessarily drinking water supply. And so tonight I'm at the start of a personal journey. I'm on sabbatical for the year 2019, and the first part of my sabbatical has been here in Hong Kong. It started in January, and I've started to think about what that Water for all looks like. So it's not a complete story. So I'm sharing with you a work in progress tonight, and I want to make some observations about the factors that are slowing the progress of this water revolution. I want to talk about some of the impediments that are slowing it down, and I want to start thinking about solutions. So that's my goal for this. And as I was preparing for this, I had a good time to think about what the conventional view was of water crises. I'm sorry, it looked fine here before, now it's not showing the images. Can I get some help? Sorry, there's supposed to be images with this slide. Let's try that again. you want to quit and restart it? Or we can plug in my computer.
Okay.
Oh, great.
Yep.
Yep, okay. So in my journey to start researching these ideas, I was very fortunate because a few weeks ago, The Economist magazine had a special issue on the water crisis. And I read this issue with great interest because I said, okay, here's someone who's already doing some of my research for me. And I read the issue, and how many of you here saw it? Okay, so a few of the people who are really into water here saw it. And I came out with the feeling, and the feeling that you get reading this special report, is that water is an institutional issue. It's not really calling out for technological solutions. The way in which we solve the water crisis is through public policy. Great, right. We're here in the public policy school, that's great. And as an engineer and technologist, I felt like, oh, I guess they don't need me. I can go home now. But I read it and I started to think, gee, this looks really familiar to me, what I'm hearing. And I thought about it some more and I realized that in 2010, The Economist had a special report on the water crisis. And I went back and found that, and I read that, and it looked very similar to the 2019 version. And I gave it some more thought and I said, well, if you're talking about a crisis and you're talking about the need for solutions, and those solutions are policy solutions, and they're not happening, we're probably not doing something right. And then I realized that the reporters in both cases had almost exclusively talked to policy people. And so when you talk to a policy person about a problem, the solution to the problem is a policy solution. And when you talk to an engineer about a problem, the solution to a problem is an engineering solution. When I gave it some thought, I realized from my research on Water 4.0 that these problems are always solved by a combination of the two. And by bringing together technologists and policy people, you can find innovative solutions to problems. And that's the kind of way I want to think about this problem of Water 4.0, because relying purely on technology or purely on policy doesn't seem to be working. So that's my first observation, is that the conventional view of the crisis is to lump it all together and say, water is water. What I want to do tonight is I want to break that apart. I want to break it into pieces and think about, I guess, a theory of change, about how change is going to come to water systems. And I want to think about it the way someone thinks about building up a business. Because if we just think about it as a humanitarian effort, it's going to move quite slowly. But if we think about it as a business that will scale and that other people will be able to join in and build, it will happen a lot faster. So my first observation is water is too big for simple answers. We can't just say all water is water. I just showed you people who are wealthy, who live in cities, have essentially solved their problem. But there are many more people who are suffering through water crises. And so I have this idea here that we start with this idea of wealthy cities that have water scarcity, and they invest in new technologies and discover things about how to provide water. And just like the early adopters of electric cars and the early adopters of computers and the early adopters of medical devices, they're willing to pay a lot of money to have that improvement in life. And as they pay that money, they create technologies, and the prices of those technologies drop, and they become accessible to others. So where we are now is we have to think about this first blue arrow. How do we take the solved problem of Water 4.0, providing water for wealthy cities, and give it to the cities that don't have quite as much wealth? So that's one of the things I want to do first, is think about how to make this accessible, and clearly making it less expensive is part of it, but there are other things we can do to share this technology. And then after that, when we succeed with that and build a larger industry, and we drop down the prices and we take advantage of economies of scale and technological know-how, we solve these other two really hard problems. And these two hard problems are providing water for growing food, particularly for irrigated agriculture. And I'll differentiate tonight between rain-fed agriculture and irrigated agriculture, another kind of thing that bothered me about those, kind of lumping it all together, because there are really two types of water used to grow food. And then we'll think about cities in developing countries, people who really don't have the means to pay for any of this technology, even if it becomes 30 or 40 or 50% less expensive. So that's the theory of change I have. There are other ways to attack this problem. You can attack it from the bottom up. You can think about simple solutions for people in developing countries, and they can build those and take them. And there are a lot of good things going there, like the Gates Reinvent the Toilet Challenge is a good example of that. But this is a different way, and this is a way that I don't see too often being talked about. My next observation is that water is unevenly distributed around the planet. I think we all know this, right? You take geography as a primary school student, and you know there are deserts, and there are mountains, and there are different amounts of water in different places. But more importantly, there are different numbers of people in different places. And there are ways that those people use water in those places. So it's an overlay of climate, where does the rain fall, and people, where do people live and where do they grow their food. And so the one that I think is most useful here is a measure that the hydrologists use called the blue water stress. So this figure comes from a 2014 paper from Nature Climate Change, in which the investigators looked at the blue water stress in the years between the years 2069 and 2099. And blue water stress is basically how much water do we have and how much do we need. And when we don't have much water, so like when the ratio of the amount of water to the amount of water we need exceeds 0.5, we're in trouble. And so the red parts of this global map shows you the parts of the world where there's water stress according to the Blue Water Stress Index. So it should be no surprise, the Southwest United States, the Mediterranean region, South Africa, India and Pakistan, and parts of Asia. You can see China, and then you can also see like the Murray-Darling Basin in Australia. So those are places we all have some sense, if we're water people, those are water-stressed places. But that's not the end of the story. If we're going to start by thinking about cities, let's think about cities. Let's think about the unquenched thirst of cities. And so I came back thinking about this to something called the Willie Sutton's Law. I don't know if most people here, do you know what Willie Sutton is? You do? Yeah, so this is a guy who was a bank robber in the United States, and they were interviewing him after he got caught, and they say, Willie, why do you keep robbing banks? And he said, that's where the money is. So Sutton's Law is you go look where the money is, and to me as an engineer, if I want to think about pioneering new technologies and building them out, I need to find out where people are going to spend a lot of money on technology. So, for example, the World Bank or USAID or one of those groups might build a reservoir somewhere. They might spend a lot of money, but that's not a major investment in new technology. New technology investments in the water sector tend to happen in cities. And so this figure, which comes from a 2018 paper, shows you, I guess, the water stress in cities between the years 2041 and 2070. The figure on the left is surface water. The figure on the right is groundwater. And the colors here correspond to different things. So for surface water, it basically is red means if water supply for cities is your first priority and you don't have enough water at least 1 month a year, your city's red. And the green one is if it's your third priority, if it's after agriculture and industry, would you be stressed? And the idea here, and what they looked at was about a quarter of the world's cities. So it only accounts for about a little under 1 billion people because it's so hard to find this kind of data. And that's why the cities are kind of randomly distributed. But the takeaway point of the surface water side is that in the years 2041 to 2070, somewhere between 1/4 and 1/2 of all people living in cities are going to be living in a city with water stress if they rely on surface water. And the figure on the right is, again, out of these 450 cities, it's the cities where the groundwater is going to be falling. And red means it falls a lot, yellow means it falls a little, and orange is somewhere in between. So about half of the cities that they were able to get data on, the prediction is in those years they're going to have a decreasing water table, which you can't do forever, right? Eventually you run out of water. If you look at the data now, you don't put climate change and population growth in, the numbers are about half. But I think it's fair to say that somewhere around 20% of people live in cities now, live in a city with water stress. And because people are migrating to cities and because of climate change, in about 40 or 50 years, that number will double. So about half the people living in cities are going to be under water stress, and that's accounting for the existing infrastructure that's delivering them water. So they're either going to have to build more reservoirs and dams, or they're going to have to use less water per person, or they're going to have to come up with some sort of innovative supply like Water 4.0. So that's why I want to look at cities, because that's where the money is, that's where the demand's going to be. Now, I talked about Water 4.0, and if you weren't here for one of those two talks, or you didn't read the book or talk to someone about these ideas or have familiarity, I talked about my experiences, and many of these experiences are in California. So the three examples that are pieces of Water 4.0 that I shared with people are, starting on the left, seawater desalination. That's a picture of the seawater desalination plant that was built in San Diego. It's about 200 million liters per day of water. It's relatively inexpensive because of the advances that have been made in seawater desalination. So it was cost competitive with existing sources of water for California. The bottom, the groundwater replenishment project, or this idea of potable water reuse, that's something that we do in the Western United States. We take those sewage from our sewage treatment plants, we treat it, we put it through reverse osmosis, we shine UV light and hydrogen peroxide on it, and then we put it in the water supply. So in Orange County, a city that's south of Los Angeles, about 80% of the wastewater now is treated and reintroduced to the water supply. And then on the top is this example of stormwater harvesting that's being pursued by the city of Los Angeles. In Los Angeles, they're building these stormwater capture facilities, and they're not doing it to prevent urban flooding. They're doing it because they want to capture that water and introduce it into the drinking water aquifer. So this is taking that dirty, nasty gutter water that you have in a city when it rains and making that into your drinking water supply. So these are the tools in our arsenal for Water 4.0 that I want to bring to those other cities. And so the way I want to think about this is I want to show you a plot of per capita GDP, this is adjusted for purchasing power, versus the population of cities. And the colors on these different figures show you the region of the world that we're thinking about. And so up until now, like the story I was just telling you on the previous slide was about the cities in California. And so you can see San Jose and San Francisco, basically the San Francisco Bay Area, Silicon Valley and San Francisco, very wealthy cities. No problem paying for it, relatively small size. Los Angeles, maybe not quite as wealthy, but larger, so somewhere about 12 million people in the Los Angeles metropolitan area, and then San Diego, where the desal plant was. And then you can see three other, outside of California, we have Atlanta, where they don't have enough water and they're pursuing potable water reuse. Tampa in Florida, where they built the desal plant, and El Paso, Texas, on the border with Mexico, where they're doing potable water reuse and brackish water desalination. So the US, you can see, wealthy, but the cities span quite a range of wealth and size, and they're adopting different strategies for Water 4.0. If we think, and I couldn't find a place to put Singapore other than to lump it with Oceania. I hope I don't insult any Australians or Singaporeans. I don't know who should be insulted, but I put them together. And they're all pretty wealthy. And if you know anything about Perth, their drinking water now is coming from seawater desalination. They're pursuing potable water reuse. Singapore has the 4-tap strategy. And again, they're weaning themselves from reliance on their Malaysian imported water. And I think that now that Australia is back into a drought, Sydney and Brisbane, if they needed to extend their water supply, would probably follow suit and do the similar kinds of things as the other Australian capital cities or Singapore. In the Middle East, whether it's in the Arab world, like in Kuwait City, or in Tel Aviv, in Israel, it's all seawater desal all the time. So the water supply in those Middle Eastern countries is almost all seawater desalinated now, and that seems to be working for them. So these are the places that have Water 4.0. Let's think about some of the others. So let's look at China. You can see here, Hong Kong, wealthy, right? So if Hong Kong had a true water security issue, I think the income or the GDP of Hong Kong would support some of these technologies. But when you look at other Chinese cities like Shenzhen or Guangzhou or Beijing, they're not quite as wealthy yet. And so for them, Water 4.0 might be a little out of reach. But as they get wealthier and as the cost of these technologies get lower, it really becomes quite accessible. A similar story in Mediterranean Europe. If you think about Barcelona or Athens or Istanbul, all cities that have water stress, they're not quite as wealthy as the Australian or American cities, so that might be a little bit of a challenge. And then if we look at the mega cities in Latin America, like Sao Paulo and Mexico City, two cities that have extreme water stress and that are larger, again, it's a little bit out of economic reach for them. So you have this group of cities in the middle that if we were to drop the cost of Water 4.0 by 50%, yeah, that would seem to be something that would be affordable based upon the spending that's already happened in other parts of the world. And then you have these orange triangles down here and that funny orange shape there. And these are the cities that are the places where they're developing cities in Asia and Africa, where the per capita income is quite a bit lower. And now you'd say, well, now we'd have to drop the price of water by Water 4.0 by 80 or 90% to make this attractive. And that might not be possible in the near term. But that's the second step in this process, right? The first step is going for those industrializing cities. The third step is going for places like Mumbai and New Delhi and Bangalore. Okay, now before we kind of start thinking about solutions, I want to make another observation. And this is an observation about agriculture. And one of the things that you find confusing if you read those articles like the Economist special report or just a general introduction to agricultural water use is that they often don't get into the detail of rain-fed agriculture versus irrigated agriculture. So this figure I like very much. It shows you in green the places that rely upon rain-fed agriculture. And rain-fed agriculture is just what you think. So those dark green places, 75% or more of the food that's grown is just relying on the rain. And so when someone says we need more efficient irrigation technologies, they're not irrigating at all. So they're not going to benefit from more effective irrigation technologies or crop rotations or something like that. They're beholden to the rain. And then if you look at the blue places, those are the places that have irrigated agriculture. And one of the things that becomes evident to me when I look at this a little more carefully and think about which of those blue places grows a lot of food, it's places like the American West, like California and Texas. It's places like China. It's places like the Murray-Darling Basin in Australia. These are wealthy places where water is a commodity that allows agriculture to grow, and that agriculture often gets shipped all around the world. So it's not necessarily subsistence farming. And then if you look at, the Arabian Peninsula and the northern part of Africa, maybe they do have irrigated agriculture, but they're not growing a heck of a lot of food. Another way to look at this agriculture problem, and again, the green places, if we were to develop some more water storage and irrigation, we might be able to help people who are now relying on rain-fed agriculture make it through drought periods and grow more food. But that's the kind of thing that the World Bank and the Asian Development Bank thinks about. It's not the kind of thing that people in California or Australia think about when they're in the agribusiness area. Another thing to think about is this concept of virtual water. How many here heard of virtual water? A few of you, not enough policy students. Virtual water is a very simple idea. It's the idea that when you grow food in one country and export it to another, not only are you giving them food, you're giving them water because they didn't have to use that water in their home country. And so this figure, and there are many like it by researchers, it started around the year 2000, this area of research. So there's been about 20 years of research on this, showing that some countries have ample water, they grow food and ship it to other countries. Other countries do other things to generate income, and they trade for that water, and they bring it in the form of food. So look at Japan in this figure. Japan doesn't grow enough food for all of its people, but Japan makes cars and makes high technology products, and it does things higher on the value chain. So it imports its food using that money it generates. And so Japan is using the virtual water from North America and Australia and even China to run its food system. And so when we think about water and water use, we have to recognize it's a global commodity. Now, another observation here to make is that rich people don't go hungry. So if there's a water shortage in a wealthy country, they're just going to import water from somewhere else. So the people who suffer in the global trade of food and grains tend to be the poor people in developing countries. And there are a lot of issues related to commodities. And what this really gets to in my mind, and these are topics I haven't fully resolved yet, is this idea that we shouldn't be painting agriculture and agricultural water use with such a broad brush and ignore the fact that it's tied to global trade markets, And it's tied to the types of food. We can't just say food is food. We have to say grains and cereals are one kind of food, and then people who are growing grapes for wine and nuts and things like that, those are luxury goods that are traded to improve people's quality of life. And so let me give you an idea of like how some of the simplifications that you might have heard about agriculture could steer you in the wrong direction. And I want to use an example from California agriculture. So I told you a little while ago that California uses irrigation for its agriculture. And in the 1970s, people used to always say, wow, California is so inefficient in the way it uses water. It does flood irrigation or surface irrigation. That's this idea that you just open up a drainage canal and you flood the fields and you grow the food. They should be using drip irrigation, or at least they should be using sprinklers and not flooding the fields. Well, that's exactly what's happened in California in the last 30 years. And it's happened in California not necessarily because of water shortages, but because farmers are trying to optimize the amount of profit they can make on their land. So the farmers in California, instead of growing row crops in fields, like lettuce and things that you might get in the market, they're growing nuts. And when you grow a nut tree, when you put in an orchard, you can afford to have a moisture sensor and a computer and micro drip irrigation. You would never use that micro drip irrigation for growing field crops. And so what's happened in California is we've transitioned away from flood irrigation to drip irrigation, but we use just as much water. We're just growing more nuts and fruit and things that generate more income from the farmers. So it's not as simple a story as, oh, irrigation is inefficient, let's change to new technologies. Farmers are economically rational people. The last observation I want to make is this idea of mega projects. So one of the great faults of engineers is that they're in love with concrete. They love building things. They love big projects. They love cutting ribbons. They love showing what's possible because they're darn good at it. And the 20th century was an era of big infrastructure projects worldwide. Dams, reservoirs, canals, all kinds of structures were built. And that's happening now in the 21st century in China and India and many other places. So many of you have probably heard of the South to North project in China. It was the largest construction project in the world for a while. And there's a proposal in India called the Interlinking All the Rivers project to take the water from the north, the Himalayas, and bring it down to the water-short parts of the country. I don't want to comment on the wisdom of those projects. I just want to share some experience with California's water mega projects, just to show you that there are often unintended consequences of mega projects, and it should give us pause before we invest in mega projects. So don't get me wrong, many mega projects generate tremendous benefits for society, but they always come with unintended consequences and long-term maintenance requirements. So this is California's mega water project. It was built in the mid-1960s. It's called the California Aqueduct. In the end, it cost each Californian about $2,000 per person, adjusted to current dollars. So that's a fair, people in California, again, GDP about $60,000, $70,000 a person, about $2,000. So that's a significant chunk of money. And what they got for that money was a system to bring water from the mountains in the north to the farms in the middle of the state and the cities in the southern part of the state. And it worked pretty well. It was really successful. Except it had some unintended consequences. It caused ecological catastrophes. It basically led to the extinction of many endangered species of salmon and other fish. And now it's causing a huge problem in a place called the Delta, the Sacramento-San Joaquin Delta. This is a region where the water is entering the aqueduct to go to the southern part of the state. And because of the way the land was managed, there's been a great deal of subsidence. And now with sea level rise, that subsidence is even more problematic. And so the engineers responsible for the project have told us they have to either build a canal to bring the water around the delta or a tunnel to take the water under the delta. And that canal or tunnel is going to cost about $700 per Californian. We've grown quite a bit in terms of size, so ultimately the cost of the project is about the same as the cost of the original project, but there are more of us to pay for it. And all it's going to do is keep that water running. And if we don't build the tunnel in time and we have a big flood or an earthquake, we could lose access to that water for 2 or 3 years, and we'd have to scramble quite a bit. So when you build mega projects, you have unintended ecological consequences, you have continued obligations to maintain them and pay for them, and you can have like a pressure point where an unexpected event can cause you to lose your entire water supply. So in some ways, Water 4.0 is a little bit more resilient. Now I want to think a little bit about those cities like Hong Kong, which might be ripe for change, might be ripe for reinvention, but haven't done it yet. Maybe they have money to do it. Maybe they can see the problems on the horizons, but people just aren't sure how to do it yet. And so I wanted to think about Hong Kong because we have discussants from Hong Kong, we have people from Hong Kong, but I spent a little time reading about like some of the story behind the proposed desalination plant, or I visited the Stonecutters sewage treatment plant and heard about the plans to go to secondary. And I've seen a little bit of the harbor and bay during my 2.5 months here. And I realized that there are a confluence of reasons why the water system in Hong Kong might need to change in the next couple of decades. But people are uncertain how to do it because it's risky, because it hasn't been done yet, because when you talk to consultants, I'm sorry, I don't mean, but you're not a consultant anymore, Alice, that's okay. Yeah, ex-consultants, they want to go with the tried and true and the things that work. And so at best, they'll get on the plane and go to Singapore and see what they've done there, and they'll go to Israel, like, you know, so maybe they'll send a delegation from the politicians that say, oh, look what they're doing there, we should do that at home. But that's just the first step. Becoming aware of what people are doing in other cities is a first step in trying to understand it. The next step is having a deep conversation and learning from many others about what's possible, and then starting the conversation, what makes sense for your particular region. So it's a little like a painter, a young painter who's starting out. They are given a palette with all these wonderful colors on it, and they could go to the museum and look at the final products, but that would be really hard to do. They need an expert, they need an artist with lots and lots of experience who could give them advice about what worked for them when they were painting. But they don't want to paint the same picture because that would be copying. So they want to learn from others about what they've been able to accomplish, but they want to do it differently because they have different ideas that make sense for them. So I want to give you an example about how we in the Renew It Research Center, that's an engineering research center that I help lead in California, have taken ideas coming from Southern California about water innovations, in particular potable water reuse, and have spread them through California and nationally. So in this particular case, we started in 2015 with a workshop at Caltech where we invited some academics, not very many academics. Academics are not good at these kinds of meetings. We invited the head of the State Water Control Board. We invited some senior management of the water utilities. We invited people from Los Angeles' mayor's office. And we had a public meeting where we talked about these ideas behind Water 4.0. And then we had a private meeting where we talked about what are the barriers that are keeping you from doing this? What are the concerns that you have? Let's get it all out on the table in a format where no one has to worry about being seen saying something they have to take back later. And that started a discussion and started people thinking. And a few months after that, the mayor of Los Angeles made the campaign for his reelection contingent upon Los Angeles achieving water self-sufficiency. So now Mayor Garcetti in Los Angeles talks about Los Angeles is going to wean itself away from imported water. Now, we can't take all of the credit as Renew It. There are many different people singing the same sorts of songs in their ears, but when they hear those songs often enough, they start thinking, well, maybe this can be done, and they hire someone in their office to look at it more carefully. And the case in Los Angeles, that's what happened. Now, fast forward 2 more years, and we went up to the San Francisco Bay Area, and we started talking to our local utilities. Here we were in the midst of the longest drought in California history, and we brought the same types of people together. We brought together elected officials, we brought together the regulators, we brought together the utility people, and we had a discussion about whether potable water reuse would make sense in the San Francisco Bay Area. And that was just part 1 of a longer discussion. And this got a lot of people excited, and it led to a series of later meetings. And now in the coming year, we're launching a series of meetings to explore all the different aspects of Water 4.0 and what they could mean to water resiliency and water security at the regional scale in the San Francisco Bay Area. And then finally, the third thing we did was we pushed this out beyond California to the entire United States. We hosted a meeting at a place called the Johnson Foundation at Wingspread. This is in the middle of the country, far away from California and Texas and Florida, where all the water reuse is happening. And we invited some of the senior management of the Environmental Protection Agency. We invited some of the thought leaders from the water utility field, and we had another one of these closed-door meetings where we talked about the potential for potable water reuse to expand beyond its traditional places where it's being built to places like Virginia and Georgia and Colorado. And just 2 weeks ago, the EPA announced a major initiative called a Water Reuse Action Plan, RAP, I guess it's called, where in the coming year, they're going to work on making a national strategy for water reuse in the United States, involving not just the Environmental Protection Agency, but all the agencies of the government. So you can see how a small group of people can play a role in catalyzing change through well-targeted meetings to introduce people to new ideas, and not really an academic exercise as an exercise in socializing them into the art of the possible. And so my recommendation is that if Hong Kong or another city that has the wealth to afford to do these things is contemplating them, they should think about this kind of approach, something a little bit more methodical than just going and seeing plants in other countries and other places and reading about them, but thinking about what it means to them. Now, I want to get back to this figure with the affordable technologies, because I want to think about what it's going to take to drop that bar down and make these water technologies accessible to people who aren't quite as wealthy as the folks who've already done it. And I want to start by thinking about desalination. And when I wrote Water 4.0, I was very much influenced by this review paper that showed up in Science. And it was based on a National Academy's report where they'd looked at the energy efficiency of desalination. And this figure really stuck with me. This is the energy power consumption for reverse osmosis desalination in kilowatt hours per cubic meter. And the important thing to look at is the decrease that happened from 1970 to about 2008, and that dotted line. And that dotted line is the theoretical minimum based upon the physics of separating salts from water. So what happened over that 40-year period is that as seawater desalination, as more research was done, as people built full-scale treatment plants, as the technology got better, it became more energy efficient. But it started approaching the point where it couldn't get much more efficient. I mean, after all, an automobile's engine's 30% efficient, and we're happy with that. So getting to 70% efficiency is pretty darn good. We couldn't go any further. And that's kind of what the thought in my head 6 years ago when I finished writing Water 4.0 is, well, that's as good as it gets. Seawater desal is relatively mature. But then I started thinking a little bit more recently about the fact that it's not just the energy that determines the price of desalinated seawater. This pie chart here shows you the costs of delivering desalinated seawater amortized over the lifetime of a plant. So about 40% of the cost is the energy of desalinating the water, about 30% is the capital of building the plant, and the rest are things like replacing the membrane modules and running the treatment plant with the operators. And I said, well, you know, all we need to do to make seawater desalination available to millions of more people living in cities is drop the costs by 30 or 40%. Maybe we can do that by taking a piece out of each of these wedges. So let's think about that. The one that makes me most optimistic that we could further reduce the cost or the energy consumption in reverse osmosis desalination is not making better membranes, not thinking about anti-scaling, but running membrane desalination systems differently. And these two ideas are just two examples, closed circuit reverse osmosis and batch reverse osmosis, where you don't run the reverse osmosis system the way we run it now as a flow-through system, but you run it in either a semi-batch or a batch mode, and you end up with an energy savings due to the, I guess it's the enthalpy of mixing. I don't want to go into the physics of it here. You can read this paper if you want to learn. But the take-home point is that in the theoretical side, closed circuit RO could reduce the energy use in reverse osmosis by 37%, and batch RO has the potential to reduce the energy use by 64%. And we might not realize all of that, but this technology, and there are others out there of running desalination unit processes differently that could save us more energy. And I'm pretty confident that as this industry grows and more desalination plants grow, the market and the creativity of R&D are going to find these ways of saving money. The second one is thinking about being more innovative about the way we design desalination plants. And I'm giving you an example. I'm not necessarily an advocate for this particular project, but this is a project proposed by a company called Deepwater Desal for a desalination plant near Monterey, California. And the innovation here is a business innovation. What they propose to do is locate a desalination plant next to the Pacific upwelling, where you get a very cold seawater current coming into your intake pipes. The cold water that they get from depths is cleaner than the surface water, so they can have longer run times before they have to change the membranes or change the filters. But they also propose to use that cold water to cool a server farm. So if you know anything about what it takes to run the internet, you need a lot of air conditioning to run the internet. So their idea is, why not use some of the cold of this water to chill the machinery for running a server farm? And then it's co-located with a power station. And the idea here is that you can use the electricity during times of the day when it's least expensive. Because in California, as we've transitioned away from fossil fuels to renewables, we have cheap energy in the middle of the day. And in other parts of the world, you have cheap energy at night. And so if you could run the desalination plant at different rates at different times of the day, you could save a lot of money, not necessarily energy. And then the third innovation is an innovation in manufacturing. So there's Water 4.0, but there's also Industry 4.0. And I didn't come up with the idea of Industry 4.0. I didn't even know it existed when I wrote the book. But this idea is this idea that manufacturing is becoming more sophisticated. And as manufacturing becomes more sophisticated because of artificial intelligence and cloud computing and other kinds of technologies, we're doing better jobs making things in our factories. So the simple example, the trite example, are 3D printers, which are starting to revolutionize some areas of manufacturing. Right now, when Dow makes a membrane, they kind of just set the membrane chemistry to be the generic seawater reverse osmosis membrane or the generic brackish water desalination membrane. What if they could tailor every membrane that they make for every water treatment facility? Do you think they could save some money then? What if the membranes were different? The front end of the membrane was different than the back end of the membrane. What if they could make things with greater precision? What if you could make ceramic membranes inexpensively? All of these things open up when we think about the innovations coming down the pipeline in Industry 4.0. So I'm pretty bullish about the idea that desalination become a lot cheaper and maybe make some of those cities that can't afford it now find it to be affordable in the near future. But if you were listening to the examples I gave you of cities where they might be coming into this next generation of Water 4.0, like Mexico City or Sao Paulo, you'd realize if you thought about your geography, these are nowhere near the sea. They can't build seawater desalination plants, so maybe that's not going to work at all. I want to talk to you about fossil groundwater. So has anyone here ever heard of Libya's Great Man-Made River? Anyone? This, before the South to North project, was the largest civil engineering construction project in the world. It was started about 15 years ago, I think, to take water from the desert of Libya and bring it to the people who lived on the coast. And this water was geologic or fossil groundwater. It wasn't being recharged anymore, but it was there underneath the surface. It was like 500 meters down. But they determined that they could pump it up and move it to the coast, and it was about 10% of the cost of desalinating seawater because this deep fossilized groundwater was not salty. They didn't have to remove the salts. So depending who you talk to, Libya either has 50 years or 500 years of water that they can take from the Great Man-Made River. I bet you can't guess who made the 500-year estimate, but he was a colonel, and he's not around anymore. But nonetheless, 50 years is pretty good for a water project. It probably ends up paying for itself. So the question we ask is, where else in the world is there fossil groundwater we can access? And the answer to that is it's everywhere, but it's usually just too salty. So here's a map from a study from the US Geologics Survey, which was about this idea of brackish groundwater in the United States. So this fossilized groundwater under the surface that's too salty to drink. It's got between about 1,000 and 5,000 milligrams per liter TDS. And these dots here show you cities that are starting to exploit this brackish groundwater under the surface. So we could have a nice discussion about whether it makes sense to mine groundwater, knowing that it's not a sustainable solution, but it's happening now. So there are people actually doing it. And I wanted to talk about kind of one particular project, one in El Paso, Texas, where the arrow is pointing there, because this project is doing something quite innovative, and it's trying to solve the big problem of inland desalination. So when you desalinate brackish groundwater, it's relatively easy or inexpensive in terms of the reverse osmosis. The problem is at the end, you have this concentrated salty brine that you don't know what to do with. And you can't put it back in a river. Right now, a lot of people just pump it back into the ground. That doesn't seem very sustainable either. But this project in El Paso is actually taking this concentrate and making products out of it. So they're recovering a resource from the concentrate of the brackish water. It's called environmental water minerals. And I just heard from one of my graduate students this morning that they went out of business. So they were maybe an idea before their time. And that's how all futuristic technologies are. I also have my doubts about them making it. But what they were doing for a while, at least, was taking those salts and making not only water, but caustic soda, hydrochloric acid, gypsum, and magnesium hydroxide, and they were selling it on the market. And I think this idea will continue to grow over time, and it'll reduce the amount of concentrate that has to be disposed of. It'll be a revenue stream for these facilities, and ultimately it will facilitate more recovery of water. So I've been talking to you about kind of these ideas, pretty expensive ideas, right? Seawater desalination. I didn't talk a lot tonight about potable water recycling, but all of these technologies, hey, that's pretty expensive water, right? That is certainly some of the more expensive water that we're ever going to have. And so if you're going to invest in these technologies, it doesn't make any sense to do it unless you can engage in good conservation practices. So if anyone here has ever visited Australia or Israel or Singapore, you'll see that people are pretty good at water conservation. You don't have these crazy toilets with 25 liters of flush, or you don't have water dripping out of pipes underground. You don't have high amounts of water loss. You don't even have a lot of outdoor landscape irrigation. And what we've learned in California over the past 30 years is that we can go a long way. So during the drought period, we took a look at how much better we could get just by implementing existing technologies like low-flow showers and low-flow toilets and sensible irrigation and water loss prevention. And we kind of came up with these numbers that I'm calling here maximum conservation. So I think cities in a place like California could probably drop their per capita water use by about 30% using existing technologies. Many cities around the world could probably reduce their per capita water use by 50 or 60%. There are very few places that have reached the end of their conservation story. But then the question is, what happens when you get there? So we already know we're going to get there in California. How do you go further? And I think that there's another step. There's probably about another 30% that we can squeeze out of urban water use efficiency. And the way we're going to do that is not by making recirculating showers and making water-free toilets and having to deal with like night soil and things like that. We're going to do it by things like in-building water recycling. And so I wanted to show you a slide from a company called Tangent Company. They're a Canadian company, and they built a office-scale water recycling system at an office park in Ohio a few years ago. And this water is basically takes the water from the toilets and the sinks in an office building, and it recycles it not only to the toilets and the sinks, but also to the drinking water. And they got a permit to do this from the regulator in Ohio, and they're starting to market this product around the world. Now, it's still pretty expensive. I don't think there are a lot of customers going for it yet, but this illustrates kind of what's possible in the future as we start thinking about building scale water recycling. Probably the easier thing to do is to recycle water at the building scale and use it for toilet flushing and cooling, but it's possible to go all the way to potable water reuse. Now, finally, I want to say a few things about those countries that were at the bottom of my graph, the places in India or Asia or Africa, where even if Water 4.0 dropped in price by 50%, they couldn't afford it. And one technology or one approach that I think bears some more discussion, I don't have a lot of time to talk about it tonight. I think I'm already indulging your patience in the length of this talk, but would be to think about using the environment as part of the water treatment system. And one of the best examples I can find of this is Dallas-Fort Worth in Texas, where all of their sewage treatment plants are what we used to call tertiary treatment. So it's biological wastewater treatment and nutrient removal and disinfection. And that water goes into the Trinity River. So the Trinity River below Dallas-Fort Worth is essentially 100% wastewater effluent. And then what they do, and you can see the picture here, the Dallas, Texas water utilities pass this water through constructed wetlands, and then they put it in a pipe, and they pump it into the drinking water reservoir. So this is kind of a low-tech, inexpensive way of recycling water at the watershed scale that's been operating in Texas for going on 20 years now. And there's a similar project in Virginia and one in Atlanta in the US that is doing this, and it's a heck of a lot cheaper than the Water 4.0 technologies I was telling you about. I think that in a wealthy country like the United States, where people are quite concerned about very small risks, this technology doesn't really have much of a future. But I think in places like India or Southeast Asia, where we have opportunities to invest in sanitation, it could be part of a program of creating more opportunities to build sanitation and drinking water treatment that works kind of as a hybrid with some of the membrane technologies I've been talking about. Now, the last thing I want to talk about tonight before turning it over to our discussants is agriculture. So I said I'd say a few words about maybe how we go in the future about reaching those people who don't have the means to pay for water. Now I want to turn my attention back to agriculture. And I think that this discussion about agriculture needs a little more nuance than it's had in the past, because agriculture and water use is not really the way that an agronomist or hydrologist would think about it. They think about consumptive water use. They think about the water that's used that ends up leaving the plant through evapotranspiration or goes out in the product itself. So when we think about water, when you apply water to a field, water that goes into the plant and leaves out of the stomata, that's the price of doing business. That's the price of keeping the plants happy. And water that goes into the plant and then gets harvested and sold to people to eat, that's the price of doing business. That's consumptive water use. The other kind of water use, where the water that you apply to the field percolates through the soil, that's groundwater recharge. So if a farmer over-irrigates their field and the water percolates into the water table, that's not a problem. They've got that water for the next year. The only time that a farmer is using water poorly is if it evaporates before it gets to the plants, or worse yet, if it runs off of the field. And so when I see an agricultural operation, I don't think about agricultural runoff. I think about agricultural wastewater. And as an engineer, I think about wastewater not only in terms of its quantity, but its quality. So this is a picture of Toledo, Ohio, and the algae bloom that shut down the drinking water intakes of the city a few years ago. And lots of people now are getting familiar with this challenge of algal blooms and its effect on human health and ecosystems. And a lot of it is due to runoff of fertilizers from farms. And we always say, oh, it's a non-point source pollution, we can't fix it. Well, we have ways of treating that agricultural waste. Call them wastewater treatment facilities. They're not sewage treatment plants. They're things like riparian buffers and wetlands and settling ponds that agricultural engineers have been building for many years. So at the minimum, we could treat that agricultural wastewater and maybe pay a little bit more money for food, or maybe invest a little bit more public money and prevent these algal blooms from happening. But we could also think about reusing that agricultural wastewater the same way we reuse municipal wastewater over and over again. So what if that agricultural runoff coming off of the fields could go through a treatment process? We could remove the salts, leave the nutrients in there, and reapply it to the land. Does that seem crazy? Does that seem like science fiction? Well, it doesn't seem like science fiction to the venture capitalists in Silicon Valley. WaterFX is one of the darlings of the Silicon Valley investors, and it had this proposal of using parabolic mirrors to desalinate agricultural runoff so it could be returned to the fields in California's Central Valley. Now, I have my doubts about this project because of some of the details of it. I'm not sure it's ever going to take off, but the concept is out there in the world. And as the technologies get better, someone may come up with a better, more efficient way to do this. So I just put it out there. Again, these are the next arrows after we solve that middle problem. So in summary, even though Water 4.0 is done, the water technology revolution is far from complete. I think that we can help those cities that are ready for this transformation, that is, that are wealthy enough, that are recognizing their water security issues, by sharing experiences and encouraging long-range thinking and showing them the art of what's possible. And we have evidence that that works. We can also make water accessible to industrializing middle-income countries by lowering the cost of the technology. So if we think strategically, not just about the energy of RO membranes or preventing fouling by putting anti-fouling coatings on membranes, but if we think about the manufacturing process, we think about the design process, we think about the process engineering, we can drive down the costs by 30 or 40%. And I'm confident that it also applies to stormwater capture and use, and it also applies to potable water reuse. I think that when we think about rapidly developing countries or developing countries, we can ensure accessibility and equity in less developed countries by employing natural treatment systems, maybe alone or maybe as a hybrid with some of these more high-tech systems. And finally, I think it's a ripe time to start talking about agriculture and making it more efficient, but not just talking about having drip irrigation and things like that, but having a focus on agricultural wastewater and the management of that wastewater in part to recover the water resource, to recover the nutrient resource, and to prevent pollution. With that, I thank you very much for your attention. I look forward to a discussion and great opportunities to engage with the audience. Thank you.
Good afternoon. It's a pleasure that I can here to introduce about the policy of the water policy in Hong Kong. Maybe I can share with you back in 2008 we have formulated the total water management strategy. In fact, if you know that in 1965, we have 1963, we have a very severe drought in Hong Kong, where we have suffered from a very severe drought when we have to exercise water rationing for every 4 days for 4 hours water supply. During those days, you know, Hong Kong people suffer a lot and quite a lot of impact on the industry. And some very interesting events or activity I can share with you is, apart from the long queue of taking waters, students are wearing black uniforms. The reason why, because they can save a lot of water in washing, and also some other exercise to save water. Say, for example, in the restaurant, some people have to use limit their refilling of water, and so during those days we suffer a lot. And it is a fortune that we have the assistance from the mainland, where we have imported Dongzhang water. Nowadays, Dongzhang water is about 70 to 80% of the water supply in Hong Kong. The other 20 to 30% of the water is basically from local use. And we also take a very innovative idea to use the salt water to help us for the flushing, and so we can survive from that sort of very difficult situation. But we know that water security is a very important topic in Hong Kong. It is very important to the prosperity of Hong Kong. And so in 2008, we formulate the total water management strategy. Basically, it is emphasis on the water demand side, and then the water supply side would be the development of new water resources. First of all, it's about the water demand control. We understand the most effective way is to promote water conservation. And since then, we have introduced a lot of measures like the water efficiency labeling scheme, We have water shower, water washing machine, that sort of water using apparatus, and then we formulate a scheme to measure the consumption of this kind of resource device, and promote the market to produce this sort of product, and then promote the public to use this sort of water-saving device. And in 2018, we formulate the mandatory scheme. That means for every new pumping system, we now require the premises to install this sort of water-saving device. And so with a hope that in the long term we can, through this means, to save a lot of water. And the second one is about the water loss problem. You know, Hong Kong has been suffering from quite a large percentage of water leakage. Sometimes I would think, say for example, in Hong Kong we have a very small theme park. The reason why, because the land is very scarce in Hong Kong. And the reason why we suffer from a very high percentage of water leakage, in fact, it is quite a lot of reasons. Say, for example, the very congested underground utilities. And if you know that every single kilometers of road, there would be some 50 kilometers of utilities, then you will imagine, you will know how congested the underground is. And also because of the topography of the Hong Kong, the pressure within the network is much, much higher than other cities. We have some sort of a 60 meter to 80 meters water head, water pressure. If you look at Singapore, they claim to have a very small leakage rate. The pressure is some 30 meters only. And so what I try to say is, because of the peculiar nature of the Hong Kong situation, so we have been suffering from a very high percentage of leakage. Notwithstanding so, we have implemented a lot of measures. Say, for example, we are implementing the water intelligent network, where we would establishing some district metering areas there where we could closely monitor the flow, the pressure, and then we would know where the leakages, the water loss are, and then we would target our resources over that area. And also we would be using lower grade water to save fresh water. Say, for example, we have already 85% of the population covered by the salt water supply system. And we are further extending it. Say, for example, we are extending our network in Tung Chung area. And also we are implementing reclaimed water in the Northeast NT. By then, we would hopefully extend our lower grade water by another 5%. That is, altogether, 90% of the population will be covered by this kind of network. So we could save another 5% of water for the flushing supply. That is, we think that is the most effective way to control the water demand, because it's also economical. The other perspective we are using is about the developing further new resources, and we have been doing so. Say, for example, the desalination plant, we have been planning, in fact we are tendering the desalination plant in Tseung Kwan Ho. The first stage would be about 50 million cubic meter. That could help us to build resilient. And of course, I think today would be a great opportunity to learn more about from David about how we could improve the efficiency of the desalination plant, because to a certain extent it is not that environmental friendly in a way, because that consumes quite a lot of energy, and also the brine would also be return to the ocean, and then it could cause certain extent of environmental impact. But in any way, it is some sort of new resource that would not be affected by climate change. You know, nowadays we have been suffering from the impact of climate change very often. Say, for example, in last year, last May, we have very serious dry weather in May, and so some people in Hong Kong also worry about whether there would be water rationing again. But because we have a very secure, reliable water storage and import from the Dongzhong water, so we are confident that in fact we are safe in that last year, and also the other new type of resources would be the recycled water. As I said earlier, we have been using taking the opportunity in North Sea NT. There's a Sep Wu Hui sewage treatment plant. We take the opportunity that they would be producing tertiary treated sewage, and we add further combination and some sort of a dye so that we can produce recycled water for the flushing. Because you know, in the inland area, we have been using fresh water for flushing. That because of the pumping cost is quite a lot. Is far away from the sea, and so we would be using fresh water instead of salt water for flushing in this area. But now with the Sep Wu Hui sewage treatment plant upgrading work, then we could take the opportunity to use that reclaimed water for flushing. And also we are building another, planning another greywater recycling plant in Anderson Road Quarry, where we could collect the greywater, basically from the bathroom and the kitchen and that sort of water. Then we can we treat it, and then we produce what we call the recycled greywater, and then we could use it for the flushing in the area. And also we are also promoting the rainwater harvesting to use as an additional source of flushing water or other non-potable use. In fact, other than those, this sort of a centralized system, we are also promoting the decentralized system. Say, for example, we have we collaborate with the Green Building Council and in their BIMPAS scheme. So long as you have a recycle system within the building, they would get some sort of credit, and that would be beneficial to their building development. And all these measures, one is the demand control and the supply, and then we could hopefully get a very dedicated balance between the supply and demand. And we also look forward to enhancing our effort in the, say for example, the water conservation. We are collaborating with the academia, and hopefully we could have some innovative ideas that would help us to further improve our work in this area. Say for example, in recently we are exploring the, in fact we are implementing the automatic meter reading system, and the first one would be in the Kai Tak area. By then, when the autometers are installed, the customer can use apps to see the water consumption within their premises. Then we think that could help promote the behavioral change, and also that can help us to know the leakage within the development, because that portion is in fact quite a problem to us, because that portion of loss, if there's any, is not chargeable at the moment, because nowadays the meters are basically outside the individual premises, and not the common area are not metered. And so there would be those areas that we are looking for improvement. That is what I want to share with you about the demand and control management, and I look forward to a further discussion with David in the panel. Yeah, thank you.
Yeah, thank you very much. Mr. Chow, may I invite Mr. Alan, Alan, please?
Good afternoon or good evening, everyone. Well, when Frederick asked me how long I work in the consulting industry, I was wrong. I said I worked for nearly 4 years, nearly 40 years. I definitely have worked for nearly 40 years before I retired last year. But the first 13 years, actually, I worked for water authorities in Hong Kong and Australia. And then I joined the consulting industry. And all my career, I've been working exclusively on the water projects, clean water, dirty water, storm water. Well, when I was working as a consultant in Hong Kong, Mr. Chow used to be my client. But since I retired last year, so I could provide fairly independent view and could speak my mind. Well, I echo what David has said, that water is not only a technical issue. It's also an institutional issue. And would just like to use the limited time available to share with you why I see the institution played an important role in the management of water. Now, first, Singapore has been very smart. Singapore has been very smart in the sense that it has introduced a new terminology called new water, because before that, it's all called wastewater. Yeah, so what this terminology, new water, means is that there's no longer any distinction between what we call the clean water and what we call the dirty water. The division is very blurred. And well, we definitely have to learn from our neighbors. Singapore, in my opinion, has the most advanced management structure, mainly because they put one organization to manage the whole water cycle, from catchment control to water storage collection, to water treatment, to wastewater collection and treatment. So it's one agency responsible for the whole water cycle. That, to me, is a very, very good arrangement. I just gave you some example. Well, in Hong Kong, it's not a criticism, SW, yeah, because it's not criticism. Because in Hong Kong, we have a department responsible for clean water and another department responsible for dirty water. So typically, the way their mindset would be thinking, what is the best arrangement from my perspective to do my job? For example, in Hong Kong, we have 4 drainage tunnels. Yeah, the Hong Kong West, Tsuen Wan, Lai Chi Kok, and Kai Tak. And we have 3 stormwater storage tanks, Tai Hang Tong, Seung Wan, and Happy Valley. But have we used any of those water? No. Definitely there are a lot of limitations why that cannot be done, mainly because Hong Kong, if you look at Hong Kong's impounding reservoir, they're mostly in the new territory. So geographically, it makes it not easy, but because I have been involved in most of those projects, and I could tell you the mindset of the client is because Drainage Services Department is responsible for the collection and treatment of wastewater and stormwater. So from that perspective, you just look at the scheme which works best for you to do the job. So haven't given a shit to water supplies department. Because I was involved in those projects, so I could tell. It's just because the institutional setup, just shake your thought. It's as simple as that. So it's not to blame anyone. If, for example, you have one agency responsible for the whole water cycle, then the thinking, the consideration would be different. Okay. Now, another thing I would like to talk about is about water reuse. David, in his presentation, talked about what in future the cost of desalination could come down. So that may be the case, but I've spoken to our specialists in desalination. That probably would take another 15 years. Because right now, a lot of the emerging technology are still on band scale level. Mr. Chow mentioned about the Changano desalination plant. In the past 2 weeks, I was involved in the technical assessment of the tenders received on that for that plant. Of course, I could not disclose any of this. But one thing for certain is, although the 4 tenderers, which are well-known operators in the world, have came up with the most efficient state-of-the-art technology. But still, as far as energy consumption is concerned, to overcome that osmotic pressure, the energy consumption is still a low 3 kilowatt per hour. Yeah, in Hong Kong, roughly 1 kilowatt hour is about $1 HK. So the energy cost for the RO alone, set aside the building services, the pumping is over $3, and that is our reality. Yeah. And Mr. Chow also said that desalination is not a very environmental friendly solution because it uses a lot of energy. I agree with that. I agree with that. So, in my opinion, what we use, wastewater we use, is a more friendly option than desalination, mainly because you don't have, because of the salinity. Yeah, because to overcome that osmotic pressure, you have to pump the water to about 60 bar. But for wastewater, because it's fresh, it's low salinity, you don't need that sort of pressure differential. Yeah. And about 10 years ago, I went with a delegation comprising officials from Hong Kong government to visit a very interesting water reuse project in Virginia. It's called Aquifers. And Aquifers is very famous, and it entertains lots and lots of delegation every year because that is the first major water reuse project in the world. The water, in simple terms, is treated to tertiary level or close to tertiary level, and then discharged into a reservoir called Aquifers. Yeah. Do you know where the water goes to? The water is taken to Washington, D.C. It supplies half of the water supply of Washington, D.C. Of course, the water will be treated. So I haven't made a check whether or not President Trump is drinking the water coming from Aquifers every day. Yeah. And so I believe water reuse is a more environmental friendly solution. But then, of course, we have to overcome the psychological issue, which is the yuck factor. There are some cities who have overcome that, and David had shared the examples of some of the cities like Orange County, very well known, Singapore, which allow the tertiary treated wastewater to be used for indirect portable consumption, but there are also cities who fail to get the public's blessing to do that, and that's our example. Because Hong Kong is already using seawater for flushing, and so actually there is a limit on what we use can benefit the freshwater supply in Hong Kong. And my own estimate is that at most 5%. What water we use, if we limit it to not to use it, not to consider it for portable use, then probably at most we could trim our freshwater consumption by about 5%. But then, for example, if we are more innovative, we think outside the box, and also look into the possibility. Of course, we need the public to buy in for indirect portable reuse. Then this could very well add another source of freshwater supply for Hong Kong. And if we look at the geography of Hong Kong, Sa Tin water treatment works, Tai Po water treatment works, they already secondary treatment work. Yeah. Forget about stone cutters. Stone cutters only provide enhanced primary treatment. It's very difficult to upgrade it to tertiary treatment. But Sa Tin, Tai Po's already secondary wastewater treatment plant, and Sa Tin wastewater treatment plant will be moved into a cavern. The existing Sa Tin wastewater treatment will be decommissioned, and that provides an opportunity to upgrade the treatment process. And Sa Tin, Tai Po, very close to Pova Cove Reservoir. Yeah. So, I mean, if we could consider reuse for indirect portable purpose and put some of those water into Pova Cove Reservoir, yeah, then definitely it would add another source of fresh water supply. I always, for people who are skeptical about the quality of wastewater which have been undergone advanced treatment, I always think one of the things we could consider is that have two samples of water. One is the wastewater which have undergone advanced treatment, and another sample is the Dongjiang water. Just compare the quality of these two kinds of water. And I haven't done that sort of comparison, but that probably is the most convincing, one of the convincing way to convince people, because inland city actually have been drinking water which include, the treated wastewater from the upstream city. So, ladies and gentlemen, just want to bring up the institutional issue and the water reuse issue for your consideration and discussion later on. Thank you.
Now, first of all, I'd like to invite Professor Sattler to see whether or not he would have any sort of like feedback or observation in regard to the comments made by the two discussants. And then we open up the floor. Yeah.
Okay. Is this on? Okay, just one response, Alan. For the record, Upper Occoquan's water doesn't go into Washington, D.C., it goes into Northern Virginia. Mm-hmm. But President Trump drinks only Diet Coke, as far as I know.
Okay. But he's very flat, even Diet Coke.
Yeah, I'd like to invite everyone. Okay, if you have questions, raise your hand, and then you can make sure. Okay, could you tell us your name and who your affiliation, and then whom you would like to direct the question to? Yeah, Zhang Tu.
Hello. Yeah, a great talk and also the great seminar. And I really want to really would like to see this kind of real discussion on this. And I want to quote old Chinese saying that. 英雄所见略同. If we will translate into English, that we have same opinion because we all are smart guy. So I want to support Mr. Alan's opinion on this kind of institution issues. And if you look at Singapore, they have a PUB taking care of the two waters, drinking water, and maybe not only two water, but also natural water together. And in China now, I think most of the major cities also have just one water bureau. They take care of the two waters in a city. But in Hong Kong, due to the historical reason, we still have WSD and DSD, and also AFCD looking after some other waters, and EPD looking after the national waters. So I think maybe not that easy to merge this kind of department together. So, but that could be some good example to learn from other cities. I think PUB, Singapore, and also mainland China. I think in the past 20 years, 2 decades, they merged these kind of two water bureaus together. One taking care of the wastewater and another taking care of the drinking water, but now just one water bureau. And another one, I think also I may not that agree with the Ellen, is that if you compare two water, one is from Dongjiang, another from the wastewater after tertiary treatment, after advanced treatment, you compare the water quality, and still psychologically people may not accept that. And also some, I think, professors from academia field, maybe I'm one of them, it will say that no, that's not good enough to compare the two water because you only use the existing water parameters. So they may not be they may not be exact same. Something could be different because we don't know yet. So that's something I want to supply. And another one is that in addition to this technical aspect and also institution aspect, another one is the economic aspect. Now people take it for granted that water is cheap. You cannot have too high price on water. But it could be the truth in the old time because we have quite relatively clean water at that time. So the cost may not be that high. But think about how much, what kind of things we are throwing into the water, different chemicals and pathogens, all that kind of pollutants. And now, although we have advanced technology, but still, it's not that easy job to treat the water into water with high quality. So that's something which I want to supply, and looking forward to see, to listen to your comments. Thank you.
Yes.
Sorry, may I take the chance to respond to one of the questions about the institutional setup? And it is indeed true in Singapore, in mainland China, the Water Bureau basically comprised the water supplies and also the drainage and even the wastewater. And this sort of question I would need to bring to the Development Bureau. In fact, if you look at the Development Bureau, because both departments, water supplies department and drainage departments, are under the Development Bureau, and the Bureau would look after the two departments as well. That aside, basically they are collaboration between the two departments. Apart from various committee, in fact, we have a regular meeting between the two heads of the department to exchange views on and cooperation, collaborations, that sort of things. And one very significant or obvious project is about the IRTS, Inter-Reservoir Transfer Scheme. That scheme, I don't know whether you know it or not, it basically is to make use of the surplus from the Kowloon Reservoir, because this reservoir is, the size is not that large, and very often because the heavier rainfall, then the surplus would drain to the downstream, to the drainage tunnel, and in that case, we collaborate with the Drainage Service Department. We built a tunnel connecting the Kowloon Reservoir and also the Lower Singboon Reservoir. Thereby, we could conserve this surplus runoff from the Kowloon Service Reservoir to the Lower Singboon Lower Sungun Reservoir, where we can then treat it through the satin water treatment works. That means, in fact, the two departments are collaborating with each other. If you talk about PUB, I don't think the PUB, under PUB, there must be two divisions, one looking after water supply, one looking after wastewater, and it is head under or supervised or managed by the head of PUB. Similarly, in Hong Kong, there would be the Development Bureau who would housekeep the two departments. And so, of course, if you are looking at a perspective that, well, two divisions or two departments sit together, then maybe some sort of efficiency there may be. But in fact, in the actual operation, the two departments are collaborating with each other. That is one of my responses in the institutional aspect. Yeah. Thank you.
Yeah, I had just a response also to the comment, the institutional comment. I can think of a case where an autocratic leader took a bunch of fragmented utilities and put them together, and it didn't work. And that was Margaret Thatcher and Thames Water. So it doesn't always work to consolidate groups together. And I can think of another example where separate institutions have worked quite well, and that's Orange County, where there's Orange County Sanitation District and Orange County Water District. They're separate institutions, but just as SW said, they are collaborating together because they have one boss, and their boss is the community they work for. And so what I've observed is that sometimes it takes a politician or a strong leader to take these separate institutions that aren't yet working together and create incentives to collaborate. And I think once that happens over and over again, you see that these institutional barriers start to melt away. And then finally, a last comment about the recycled water versus surface water. I've spent a lot of time in Orange County, and the only place I've ever bought bottled water and drank it is here in Hong Kong.
Oh, yes, please.
Thank you. My name is Tesso. I'm from the Consulate General of Hong Kong. I am an cultural trainee. I have a question for Professor David, but I also would like to share my thoughts on the last discussion. Two things you mentioned. The first one had to do with the topography of Hong Kong. And for an engineer, that wouldn't actually be a minus. It could actually be put to advantage because using gravity, you can actually save cost in the pumping of water. And I was thinking that maybe the Hong Kong authorities may consider using the gravity technology to be able to reduce the cost of pumping. That's on the one hand. Even though that a lot has been said on the institutional issues, I still want to say one little thought, though. I think that it's a matter of policy. Several different parts of an institution can work together, synergize, collaborate, and complement each other and still achieve the desired goal. What needs to be done is perhaps a revisiting of the water policy in Hong Kong. All the stakeholders put together may need to sit down and redesign the template for how water is managed in Hong Kong, with each institution or each member of the institution doing a specific role that complements the other rather than drag them behind. Professor David, this is my question to you, sir. While you rounded off, you spoke about technologies that may work in Africa. And in particular, you mentioned runoff and water treatment. But you see in Africa, where there's a lot of drought, our problems will not even be about recycling or even conservation. It will most be about sourcing. Because you have the technologies that are working now are actually borehole drilling, where underground water aquifer is what people can access. And when you have very less to use, you can't even begin to contemplate how you can, recycle water, for instance, in agricultural water treatment, because you have to take factors like evapotranspiration to begin with, and that because the soil is already dry, of course, there's going to be a lot of seepage, and so what is left is not even enough to recycle. So what technologies will be more relevant to Nigeria? Taking, for instance, what is happening in Israel presently, where there's precision irrigation to the root, so that the plant can use that. And rather than look at conserving, look at recycling, we are conserving to have consumptive use that is appropriate. Thank you.
Yeah. Thank you very much. I do value very much hearing from someone with experience in agronomy and really crop science. I've seen the drip irrigation systems that have transformed agriculture in Israel, and I've seen California's drip irrigation systems, and they can do amazing things. And so there are two things here that need to be resolved. One is salt management. And so if you have precision agriculture, you have to be very careful about measuring salinity. In some places where they've had good luck with precision irrigation, they also have rainy seasons that wash the salt away. So it's going to be different in every setting. It's going to depend on the soil type and the annual hydrology. But the second piece, and I think that the one that I'm just not sure I understand well enough yet, is the difference between growing grains and cereals and growing other kinds of crops. And I've yet to see any real, the best innovations for grains and cereals are plant breeding, probably, to find plants that don't consume as much. And we haven't even broached the larger question of meat eating versus vegetarian diets, which are probably even the better way in rain-fed agriculture to conserve water. So I think it's a rich and important area. I didn't mean to break it down and imply that recycling wastewater from cities was the solution. I'm not even sure that recycling drainage water from crops is a solution. In some places, like for example, in California and along the Mississippi River in the US, where we have a lot of drainage because that's the way we farm, it seems like a missed opportunity to be sending this nutrient-laden water down into other people's water supply and into their lakes and rivers to cause algal blooms. So that's kind of the problem I think I was trying to give some new perspective on. But I agree with you. Arid agriculture is probably more one of a question of soil fertility and choosing crops correctly and getting subsidies right and trading, and in some cases, both drip irrigation and fertigation, which are both very effective approaches.
Yes, Anthony. Yeah.
If I may ask David regarding local non-portable recycling, is there an optimum number of population or size for it to be cost efficient?
Yeah, it's a great question. I think the way I've been thinking about it more recently is that every city is different. And so when you look at Hong Kong and how tight the utilities are and how small the buildings are, that's quite different from many large cities where there are considerably big pieces of land that could be used for distributed recycling. So the example I can give you from my own experience is Google and Facebook and Apple, they're building these big corporate tech parks. They want to recycle their water, and they have tremendous amount of space. And so they could build a recycling plant, or they have irrigation demands because they're going to have trees surrounding the property. Very different from Hong Kong. So I think the opportunity for Hong Kong, the two opportunities I can imagine in Hong Kong are at the building scale. So in San Francisco, there's a new ordinance that's requiring that new buildings in the central business district, which are maybe our tall buildings or your modest-sized buildings, but they're having to install in-building water recycling systems, and they're running dual reticulation systems and have the recycled water flushing the toilets. The other option is that if it doesn't work in one building, 3 or 4 or 5 buildings can come together and build a centralized facility and share the water. And in fact, the San Francisco Public Utilities Commission changed their regulations to allow that kind of district-scale water reuse to happen. Economies of scale there, but buildings don't always get built at the same time and retrofit. I think you have an incredible laboratory here in Hong Kong for trying out these different things and really getting data on the economies of scale of these different solutions. And one of the things that I imagine about the seawater flushing system is that it must take an incredible amount of maintenance to run salt water through pipes for so many years. So it could be possible that in parts of the city where the pipe works are the most corroded, that could offer opportunities to say this small block of apartments will be a laboratory where we cut off the seawater supply and use the dual reticulation piping in the buildings to try these different ideas for in-building water recycling. So I come here and I don't see a problem. I see an incredible laboratory to answer that question.
Yeah, maybe I can respond to that. In fact, the flushing supply in Hong Kong accounts, if we take the total water demand, including the flushing demand, basically the flushing demand is about 20 something percentage. It is about 280 million cubic meter. And Hong Kong is lucky because in 1950 something, we have already started to use salt water. By the term of using salt water, that means we have 2 separate systems. And this offers an opportunity for us to use other water other than salt water. And we are not that restrictive in mindset to explore opportunity to extend the reclaimed water or the recycled water to areas that are using salt water when opportunities come. Overall speaking, I think we have to take into consideration of the cost effectiveness, because upgrading the sewage treatment plant is quite costly, and that's why the reason why we can make use of we can supply reclaimed water in Northeast New Territories, because we take the opportunity that the Drainage Service Department, we collaborate with each other and understand they would be upgrading their sewage treatment plant to a tertiary level. That provides an opportunity that we add on some marginal cost, that is some combination and some preventive measures. Then we can make use of the reclaimed water to supply for flushing. It so happens that area is inland. We are using fresh water. That is an added benefit. Then we could save fresh water. And the other area in the North NT, there are new development area. We are also considering extending this sort of reclaimed water for flushing in this area. We are other than replacing salt water, that is under our exploration, and we are not restrictive to use reclaimed water to flushing only. But bear in mind, the other non-potable use is only 10%, less than 10%, that sort of order. And it would be demanding in terms of infrastructure requirements and also safety precautionary measures to allow another use of reclaimed water to these non-potable users. But we would be collaborating with other departments, say for example FEHD, where they could take the recycled water for street cleaning, that sort of things. We are very hesitant to use reclaimed water for other use, because that tertiary treated effluent is not that up to the drinking water level. So we have various safety measures to prevent cause contamination. That sort of additional consideration. And I also take the opportunity to add on about the as Ellen said earlier about the drainage tunnel that Drainage Service Department has built years earlier. The reason why we did not make use of that sort of water to supplement our, say for example, water supply, because in Hong Kong we have designated more than 300 square kilometers of land as water gathering ground. The reason why we designate these areas as water gathering ground, that means we are imposing regulation control over this area against pollution. Those drainage tunnels are not built within that sort of water gathering ground. Those areas basically is urban area, but of course with scattered population. And we have taken some water sample in, say for example, the Western Drainage Tunnel, and note that the quality is not that good. And also there would be involving quite a lot of infrastructure requirement to bring that water back to the impounding reservoir, safe against the concern about contamination. So we have collaborated with Drainage Service Department and study the case, see whether there's opportunity to use that sort of water. The successful one is Kowloon Reservoir. The others we have considered, but not that suitable. Thank you.
Patrick, can I? Sorry.
Oh,
Can I?
yes, please.
Can I add a comment?
Yes, please, Alan.
I think the question from Dr. Actually brings up the issue of centralization versus decentralization. And well, right now, Hong Kong, like most other countries, we use a centralized approach. Let's say water reuse plant, we collect the discharge from in various locations and bring it to a central plant and treat it, and then pump it, distribute it back to the consumers, which the water originate produce. But you bring up another concept, which is decentralization. Then there's constantly debate about that. But in Hong Kong, with the Water Supplies Department, the Drainage Service Department, all provide very efficient, excellent service. And the question I think we have to ask is, what are the reasons, say for developers, who have to not submit an application to the Water Supplies Department for supply of water, or supply an application to the Drainage Services Department for connection to the sewers, than to make an investment in that sort of on-site facility. So there must be incentive to do that. Just to quote an example, well, we have been talking about how the beauty of renewable energy for a long time. But up until 18 months ago, when the tariff structure is changed, which provide incentive for people to install solar panel in their rooftop, because they could then sell that renewable energy to the power company for maybe 4 times the cost, so four times the tariff. Yeah, only until you have scheme like that, which could cause people to do that sort of things. And I would say, as far as water supply, sewage services, it is still the same. Without the incentive, I just can't imagine why some developers would try to go for that.
Yeah.
Well, yes, it's difficult to consider that commercially, especially the seawater for flushing we don't have to pay a cost. And until you have to pay more of a cost, then that might be different. But in Hong Kong, the biggest landlord or party that builds the most buildings would be Hong Kong government. And it would seem that for new housing projects, this kind of local recycling should be considered. Maybe not. That's why I asked about the cost efficiency. At what point in time that this would be more workable?
Well, I can offer that we did a study that might be relevant here in Hong Kong and San Francisco, where we tried to ask this economic efficiency question, and one of the answers was it depended on elevation. So it was more attractive to recycle at the building scale at higher elevations because you didn't have to take the pumping costs. So I can imagine here at some of the higher elevations, in-building water recycling would defray the cost of pumping that seawater up the hill. And that might be a reason to give someone an incentive or a discount for doing it. So that's where what we found is that it had part to do with density and distance from the water supply plant, but elevation kind of swamped everything. And I think Hong Kong is even hillier than San Francisco.
Yeah, maybe
I'm looking.
maybe I can supplement a little bit. You're talking about the decentralization and the centralization of that sort of things. In fact, in Hong Kong, we are promoting the decentralization to a certain extent because I said earlier, we have the collaborative Green Building Council. We have the BIM plus new building scheme where if the developer installs that sort of a recycling plant, then they would get additional GFA. That could mean a lot of money to them. And this is in fact some sort of incentive. To be honest, the capital cost and also the operation and maintenance is expensive currently. And so we look forward to innovative advancement that could save costs. One thing is we have incentive, okay? The other one, the government also take the lead. As example, for government buildings, in fact, there are some 70 projects with rainwater harvesting system installed. And several of them has also installed a grey water recycling system. And that is, in fact, there's a circular within the government that even we ignore the capital investment, so long as the recurring cost is okay, can save the cost of water, then proceed, go ahead. And so we have both inside government and also the private sector, we are promoting the use of this sort of decentralized system. And also in a small scale, in Anderson Road Quarry development, because of the pumping cost, you know, it is very high level, and the pumping cost would be very expensive. We pump salt water to the hill, and so we take the opportunity. We get the source of water, that is the grey water from the development, and then treat it locally, centralized. Not a very big plant, it's something 3,000 cubic meter capacity. We can collect, treat, and we provide to them for flushing. These energy costs would be much less because we save a lot of pumping costs from the source to the demand. I think we try every sort of ideas to facilitate, to suit each case. I think I supplement that.
Yeah, we may over just a little bit, but there's a question waiting, okay? Please, yeah.
Yeah, just a really quick one. So do you think it would be possible to have this kind of experiment on university's campus? Because you have clusters of buildings, you have researchers. I guess that would be the advantage if you want to collect the data.
I think they need to get some money.
Would that be feasible? Like, would that be a crazy idea?
No, I mean, I see, so first of all, I always love the idea of doing these kinds of experiments at universities because they're part of the training of our students about what's possible, and it gives learning opportunities, and for those who aren't even involved in it, it creates familiarity with new ideas. So I think that's always to be applauded. There was a very innovative project at the University of Florida, I think it was one of the Florida universities a few years ago, where they made a dormitory that recycled all of the water that was used in the dorm, and it became a way to study it and student behavior, and it was quite fascinating. I could give you the link to it later.
In fact, WSD has that sort of experiment or pilot project in the Tin Shui Wai, our office. We have a water resource education center. In the center, you will see how we collect the grey water, and then we recycle it for reuse. And that is some sort of education center where we can help promote and teach the students and the public. And that would be open later in the middle of this year, and we will welcome all of you to visit the center later.
Well, it's like time now is like 6 o'clock. Yeah, so on behalf of the Center for Water Technology and Policy, I'd like to thank all of you for coming here this afternoon to attend this seminar. And I'd like to ask all of you to join me to thank our speakers and the discussants.